It's a great pleasure to welcome you all to this first workshop of TC222, Geotechnical BIM and Digital Twins. My name is Raymond, and I'm chair of the TC, leading this together with Mickael in Paris, Jelena in Birmingham, Raymond in Hong Kong, and Mats, which is also sitting here in Oslo. First, some practical information. It would be really nice if you all can mute your microphone. I'm also able to mute you all, but it would be nice if you could do that. The workshop is recorded, which means that we will publish it afterwards. The TC has today 40 members, while the amount of people who signed up for this workshop is more than 150. So a kind request that you contact your national member society of the ISSMGE to become members of the TC. We need more members, and remember, you will easily get the information on what's going on in the TC in the future. Paul first, presentations afterwards, experiences and results from Paul at the end of the workshop. Are you ready, Mats, for the first presentation, talking about modern workflow for BIM?
Yes. Let me share my screen. Hello, my name is Mats Kahlström. I'm a geotechnical engineer working at NGI, the Norwegian Geotechnical Institute here in Norway. And I've been given the pleasure to kick off this series of presentations by talking about parametric 3D modeling for geotechnics. And this is something that I believe defines a modern workflow for BIM, or building information modeling. And as geotechnical professionals, we often spend considerable time creating 3D CAD and BIM models, at least I do, for our project deliverables. So a few years ago, to make this process more efficient and reduce iterative modeling time, we started to work with parametric design tools. Since then, parametric modeling has opened up a world of possibilities, not only related to creation of 3D geometry, but also to build complete BIM models, perform analysis, get cost estimates, and do as-built verifications. And I will showcase some of the things we have worked with recently by creating a new imaginary example project. And the codes and scripts shown in this presentation have been developed by two talented engineers at GeoVita, Nikolai and Paul. And GeoVita is a small Norwegian geotechnical consultancy, and also a few of us here at NGI. So what is parametric modeling? In short, it's kind of a script that defines work processes and automation of instructions to a CAD software. In this presentation, I use the CAD software Rhino and its built-in visual programming interface Grasshopper. And Grasshopper can also be used with several other CAD softwares such as BricsCAD and Tekla. And if you work with Autodesk, you can do the same thing using their visual scripting program Dynamo that can connect to Revit and Civil 3D. So like in this video example here, I can create a script that builds a row of 3D columns. So I created a point, and then I create some number sliders, a cylinder object, and then a few sliders to control my column, an X vector, and a linear array. So I simply connect a point to a cylinder, assign a radius, and then also a length. And then I say that I want a set of columns with 5 meter spacing, and I want 20 columns. And then I can copy my geometry like this. And the thing here is that I can now adjust my sliders and all the objects will update. And I can also move the point of origin in the model, and all the other objects will follow accordingly. And that's the basic principle of parametric modeling. And the parametric workflow we aim to use in our projects puts the 3D model in the center of the work, and not just something we do as a byproduct of the geotechnical design at the end. The entire workflow, when used fully, is a series of Grasshopper scripts covering input of layers from the ground model and building data to various scripts for the design phase, and finally to manage the as-built data received back from site. And as you can see there in the middle, we can take out cross-sections from our scripts and send to, for example, Plaxis to do a design analysis. And the nice thing when building these scripts is that they can be reused from project to project. So when you start on a new project, it is quite quick to get the basic model and design up and running. So let's try out some of these scripts on an imaginary hotel project in downtown Oslo. And the client wants to build a new hotel with the 3 stories of underground car parking here. And we, the geotechnical engineers, say no problem, but it will require a deep excavation. And I showed the script a few slides back how to create the columns. And in a similar way, we have made scripts that can build an entire deep excavation. And with these tools, we can in minutes create the full 3D model to the client, get a grip of costs and risks, and engage in dialogue with the client on the proposed solutions. The picture to the left shows the full script, and the resulting model is shown to the right. So let's start modeling. I'll show a video that this process shows the process in real time. The script has some Norwegian names in there, but I think you will manage to follow anyway. So first we import some input parameters, CAD objects, such as the excavation outline, as you can see, and then a terrain model and a bedrock model. And I can pan and view the models here in the Rhino viewport to my left. Then I have to add a function to transform between local and global coordinate systems. And that's because we use Tekla afterwards. And next, I add a function to create the retaining walls. For this, I need to connect the excavation outline, the bedrock model, and the terrain model. And as you can see to the left, instantly, we have created a model of sheet pile wall. I can check out here, or I can open it in Tekla and also check it out. And here we have assigned the predefined type of sheet pile, but this is something we can also vary in the script by changing the inputs in Grasshopper to the right. So to add a few beams and an anchor system, I start by adding a small script that defines at what level I want my anchor row and connect it in a series to the retaining wall script. And now you can see a green line to the left that defines my first anchor row height. Next, I add a script that creates tieback anchors and connect it to my anchor row level. And I also need to connect the bedrock mesh. And oops, you can see the anchors are being generated inwards, so I quickly change that. And we can now review the tieback anchors in the Rhino viewport. And we can also open it up in Tekla and have a look at it there. And now if the client would come and ask that I want to modify one of the corners of our excavation, I can just drag a reference point and the entire model will update accordingly. And that's also one of the beauties of parametric modeling, that everything is connected. Parametric modeling can be used for more than creating 3D objects or BIM models. For example, we can create a script that performs some kind of analysis or calculation, either directly in the software or using Python or a C# functionalities within Grasshopper. And in this example here, we see a bedrock mesh that is being colorized based on the subjective uncertainty based on the distance from each mesh cell to the nearest borehole. And to show this a bit further, let's calculate some ground settlements surrounding our new deep excavation. So for this script, it calculates ground settlements based on wall deflection and an assumed groundwater lowering and influence zone. And I use a wireless connection to import the required geometry from the script, the previous script, and then I assign the depth of the excavation to 10 meters. Next, I have the option to modify some of the soil input parameters needed for the settlement analysis using the Janbu method we use in Norway. And I decide to check the results for a 2-year consolidation time that I calculate based on Terzaghi theory. And we check the results for a 50-meter grid cell size. So here we can start by reviewing a few of the background layers. So this is the bedrock model. We can see some of the buildings that I import from OpenStreetMaps. We can also turn on the terrain layer. So it looks fairly good. Now, yeah, I also added a model of our very large funny hotel. Now let's run the script. So we activate it by clicking here. And then it takes a few seconds to run, and it calculates the settlements in a grid pattern that you will see pop up here now. So we can inspect the results. First, we can review the depth to bedrock colorized for each grid cell. And then we can see the pore pressure reduction zone of influence in case we have drainage to the excavation, and also the amount in each grid cell in kPa. And then we can see the total vertical settlements for each grid cell colorized based on the ranking criteria. And then also we can review differential settlements for each grid cell. And in this case, since we have a very large grid cell size, 50 meters, we get very low differential settlements. So that's pretty good, but it would probably be more if we had a smaller grid size. We can also check contour lines to see the settlement direction. Now, I can also perform this analysis on the building objects itself and not on the greenfield terrain grid. So we'll do that, but first I click off some of our layers that are visible. And then I just change here in the drop down to buildings. And it will rerun the analysis and perform the same analysis for the buildings. So here we can see the pore pressure reduction zone of influence around the excavation, but now the colors are on each building. And in a similar way, we have now the settlement plot in 3D, and you can see there's a two buildings there that are orange. So we might have to do something with our design. So then we need to update the model. And based on the settlement analysis, it seems appropriate to update our design to reduce the impact on the surrounding assets. And we have convinced the client to opt for a single underground story instead of 3, therefore changing from a 10-meter deep excavation with 3 anchor rows to a 4-meter deep excavation with 1 row of internal inclined struts. And we can do these modifications directly in the script, like I'm doing now, so that our BIM model reflects the latest design. And it's a bit speeded up here, but I basically then just hide the anchors and add a script to produce both a series of inclined struts and then a concrete base slab that we use for the inclined struts. And the final model is shown here. We have the now shallower excavation with some inclined struts that are anchored towards a base slab. And now that we have established a detailed 3D model, we can view it in a BIM viewer like Trimble Connect, together with other discipline models to perform class checks. And we can also inspect the property set, something that we can either add directly in Grasshopper to the objects and to the model if we produce an IFC file from Grasshopper, or we can do it in a third-party software such as Tekla and then export the IFC model from Tekla with the property set. Design review and third-party control can be done model-based, where the reviewer can check model maturity index or LOD. We can check the property set and see if the model geometry looks okay with respect to the terrain level and the bedrock level, for example. And another way to view a model is by using a virtual reality software. So here in this video, we can try that out. And it's quite easy to move around in virtual reality and make checks of geometry, collision, properties, and interdisciplinary control. And contrary to just looking at the model on a PC screen in 2D, you get a bit more realistic impression of scale and size when you stand in the excavation. And we can have a virtual meeting with other people together in this virtual environment, and we can have a look at different objects and do measurements to check if it all looks good and what we want to build. So here we are checking to see the length of this beam, and then also to go in and have a look at the property set for this object. It's in Norwegian, but it looks pretty okay. And here we have the project property set. You can see some quantities. I guess this depends on which VR software you're using, but I guess this would be fairly standard functionality. Yeah, we can also check the length here and yeah, play around a little bit. If needed, we can take out the bill of quantities to Excel directly from, for example, Trimble Connect, or we can create a script in Grasshopper that automatically generates a bill of quantities based on the current configuration of our model. And this is something we've just made as an example here, but we are working on refining this a bit. So let's call it 5D. And here we have quickly made some input data for example, steel weight and other parameters we need to compile quantities. And the quantities, yeah, we have different mixture values for lime cement. And the quantities can be summarized in this view here. It's a very quick mockup. It's in Norwegian, but for example, the current model now, we see that we have about 7,500 square meters of sheet pile wall, 360 meters of beams, and then 908 meters of internal struts. We could also progress this one more step to compute some sustainability metrics for CO2 emissions based on our model geometry. And since I know the ground conditions in Oslo often has very soft clay, we probably need to add some ground improvement using lime cement columns. So we can add this by dragging down a new script component to create a grid of lime cement columns in our excavation. So here we produce a triangular grid, but I want to change that to a square grid instead. So like this. So let's check the results. And again, the text is in Norwegian, but to summarize, the combined contributions then from sheet pile wall, strut system, and the ground improvement is about 4,400 tons of CO2. And the ground improvement makes up about 50% of that. And as a fun note, it can be converted to flights from Norway to Thailand for me and a colleague. And for the same amount of emission, we could make the return flight 777 times. Once something is constructed on the site, we can receive back production logs from the contractor, in this case lime cement columns, and we can import that into a parametric script and generate as-built models. And this example shown here, it's an actual project we did last year. The as-built model is shown there to the left. And to verify the design, we have created some scripts to analyze and perform a review. And to the top right, we have color-coded each column based on the cement consumption. And to the bottom right, we show clusters of columns with length deviations. And this is also done in Grasshopper. So to finish off with our example hotel project in Oslo, as a final thing to show when we already have the models, why not create a little video on how the construction site might look like? And I think there's a sound on this. See here. I'm not sure if you can hear anything, but let's turn it on and then we can see a slight panning. And as you see, of course, we had to have a golden sheet pile wall since we had unlimited budget on this project. Thank you for your attention.
Thank you, Mats. I was about to comment on that golden sheet pile wall. It's not something that we usually use in Norway. Next one up is Mickael, who's going to talk about geotechnical data standardization with IFC and OGC. Hi, Mickael.
Hi, Minus. Do you hear me?
Yes, we do.
Yeah, cool. So I will try to share my screen on live.
Yeah.
Do you see it?
And yes, we do, but not in presenter mode.
Yeah, that's the next steps. Should be happening now.
Perfect.
Okay.
Thank you.
So, good morning, good afternoon, and good evening, everyone. My name is Mickael Beaufils. I'm the vice chair of TC222, and it's also my pleasure to welcome all of you and perform that presentation. We will not have so much nice thing like Mats presented with 3D representation. I will go back to very basic thing like data exchange and the issues we have with formats and why we need standards to reach what Mats presented, for example. So I will talk about something called the OGC Geotech Interactive Experiment. So OGC is an organization that is performing some standards for the geospatial domain. And I will talk about this specific activity we have and that is happening now. So what is the Geotech Interactive Experiment? It's an effort to federate the geotechnical community around stormwater. So you may already know that picture about how standards proliferate and our temptation to try to do one standard that cover everything. So in that project, we did not go into that direction. We wanted just to see what are the benefits of the existing standards and how they can work together in the domain of geotech. So we started this activity in 2022 on February, and we expect to end in the mid of 2023. So OGC is hosting that activity, and I will explain you why OGC is doing that. So the motivation we have is to do some digital continuity for geotech. This is to connect GIS and BIM, but it's also connecting the geoscience and civil engineering. You know, geotechnics is between the two of them. Some may have some discussion about difference between engineering, geology, and geotechnical engineering. Well, we have to address this connection that is between geology, geoscience, and civil engineering. And when you look at how those two are addressing the digital transition, what are the standards? You see that for civil engineering, there is one standard that is relevant, that is Building Smart International. Well, the most famous one, performing OpenBIM. And on the other hand, you have the standards from OpenGIS. And regarding, for example, geology and hydrology, they are endorsed by the International Union of Geological Science. And so they are also used with the OGC standards. So if we want to connect civil engineering and also the standards we have with geoscience, we have to think about connecting the standards from Building Smart International and also the one from OGC. And we also have some specific standards that are very focused on the geotechnics. Two of them are AGS and DIGS, that you may already know, that have been designed especially for geotechnical people. And so the idea in the Geotech IE is to consider trying to work with those four standards. I mean, this is not exhaustive, but we try to do something together because we have a common wish, that is enhance data exchange for geotechnics. This idea dates back to 2019. Indeed, there was some action in order to enhance the geotechnical standards, especially for the BIM domain. And there was a workshop organized in Paris, in which we, as members, identify that, well, it would be cool if we could speak the same language for geotechnics and try to connect ourselves and see what we could do together. So this is happening now with the geotechnical experiment. That is how we will perform this activity. One important thing is that we do not only think about the exchange between softwares, and we also think about having the geotech data more central. This is something that will be quite important for digital twins, because you will think about data that are often updated. And so if you have to exchange a file each time you have an update, then you will not have a digital twin that is easy to maintain. So you have to think about different way to access your data and have them in a central position that can be addressed by the different software or the different people that may have interest in them. So we are speaking about fair geotech data, which stands for findable, accessible, interpretable, and reusable data for geotech, and that's the goal we are trying to reach, especially with the Geotech IE. So in the Geotech IE, in more details, I would say that we have different kind of work packages. We have some that are community-oriented and trying to do the connection between different people that have different background, different softwares, and also trying to have the software providers looking at what we did and try to implement what we propose. So this is a work package 1, 4, and 5. So we are doing a common conceptual model I will describe just after. Also a technical paper that is already available that I will share to you at the end of this presentation. And we will do some implementation guide for software vendors. The idea is that those people in the group will try to speak as one voice, and we expect that the software vendors may find their interest in, okay, trying to build one solution that will cover the needs of the people from geotech domain. So that's for the community-oriented goals that are very connected also to the goals of ISSMGE TC222, trying to federate, do some guideline recommendations. And on the other end, we have some technical-oriented goals that are to propose effective solutions to enable digital continuity between GIS and BIM. So we are defining the standard. This is not done, especially in this Geotech IE, but in connection with what is done in BSI, also in OGC. And so in this specific project, because it's endorsed by OGC, we will work also on the extension of the OGC geoscience standards. As I said before, they are very convenient for describing geology and also hydrogeology, and there will be some extensions to cover geotechnics. There will be also some documentation that will be provided in order to provide more easily data through OGC APIs. And we also have an implementation forum that is about to demonstrate how those standards can work together and fulfill the exchange requirements. So regarding the common conceptual model, the idea is, okay, we have members of all those organizations, all those formats development, and they are sit all together in order to try to define what is geotechnics, what are the geotechnical data that are relevant to be described and to be exchanged. The idea of this conceptual model is it should be agnostic. It should not be dependent of the softwares and the formats that are will use them. I mean, it is about how do we describe geotechnics? What are the correct wordings? What are the core concepts in order to describe what we do and what we intend to describe? As you can see, this common conceptual model should be common for all those formats and standards. And the AGS, DIGS, OGC, and IFC standards should be some realization of this common conceptual model. It is very important because it would enable the transition between those different platforms. So if you imagine to go from GIS to BIM, then you will need some common language, common conceptual model. And that's exactly what we are trying to do. So at first, there was, when we defined the standards for GIS and BIM, this idea that, well, a BIM model or model in general is composed of objects or features suited to attributes or properties. So the intention is to map the subsoil. And so you will identify some discrete objects, and you will want to propose and attach some properties or attributes. So the first thing to do was to identify those objects. This work was performed before the Geotech IE. It was performed in a project in France called MINE, but it was also done in the Building Smart National IFC Tunnel project that was also addressing geotechnics. So we look at the models that were made in this context, and we identify what are the key components, what are the key elements that are inside those models. So different people from the projects show what they already have. The idea is not to build something that would be very different from what you already do. We expect to have a smooth transition from the existing to this new format, new way of defining data. And so, for example, we shown that, okay, for some geological models, there are these important components of geologic units and also contacts and faults. And we did it with all we had under the end. So different kind of model, different kinds of presentation. You can see some are 3D, some are 2D, and also depending on the context and the purpose of the model, we identify what are the key objects we should try to have in the models and describe. So then there was this question, how should we organize our objects? So after that activity, we have a list of objects, and those objects have things in common, and we wanted to put them together. In order to organize this, we didn't start from scratch, and there is something that is already used in the MIND project and also used in the IFC tunnel project, is the use of these books from the ISSMGE TC222 project. So the IFTES is a French association of tunnel and underground space. It's a French ITA, I would say. Last week there was the meeting of ITA, WTC. And what was found as relevant by the community, the MIND project, and also the people from BSI International, Munich Smart International, was to use this organization of data based on book A, that are the observation measurements, the book B that contains the models, interpretations, and uncertainty, and also the book C that is a design report with the projection on what should be built. And so you also have this dependency between the book C, the book B, and the book A. So this is how the ISSMGE TC222 data are organized. If you do the connection with our objects that we identify and also the formats, that gives you this kind of array. So on this table, you can see that what are the components we identify from book A. So we call them the observation supports or sampling features. So you can expect to have description of borehole, material sample or specimen, trial pit, observed zone. And attached to those observation supports, you have some observation measurements that are performed, so in situ tests, laboratory tests, monitoring. And those, for the book A, those there are different formats that already address them. So there is the formats from AGS and things, but also OGC and Munich Smart International are addressing this domain or intend to address this domain. So we will have to find some way to communicate each other in order to facilitate transfer of data from one of those formats. For the book B, that is the modeling, you have here different kind of models that have been identified and their components. So the components for geological model, hydrological model, also a geotechnical model that will be introduced. So the intention from OGC and Munich Smart International is to be able to describe them, and interpretation will be associated to them. There is also this intention from AGS with AGSI to address it. And for the book C, which is a connection with the construction, you have here this concept of alignment, typical design area, and geotechnical zone of influence that have been identified by OGC and Munich Smart International in order to describe the context of the project that should be built. Next things, when we identified the objects, was to discuss their definition. So what is a borehole? What is a trial pit? What is what is a geological unit? It may sound obvious, but for everyone, but when we share our obviousness, it seems that this is not so obvious. So we have a GitHub that enables to discuss those things. We also identify the attributes we want to attach to those objects. And here you can see the tables that show the attributes we have in OGC standards, in IFC standards, in AGS standards, and DIG standards. The idea is to see what is common and what will be part of this common conceptual model. Big discussion we have was about how should we describe the observation, measurement, and sample. So this is a key discussion we have. It's about how should we provide the result from some procedures, what should be the granularity of it. And so the intention is to try to do something identical for interpretation and observation measurements in terms of structure. Another topic is the semantics element. So there is also the wordings that are used in the different formats. So for example, definition of what is a dry density. We look at what was proposed by the different standards, and the idea is to do some bridges and to do some connections in order to be sure that we are speaking all of the same thing. So same, it's performed like with the kind of tables. As I said, big discussion about the procedures and also the links with the results, the level of granularity we should have. And the reason why we try to bridge those things is about trying to define some APIs that will enable to deliver the geotech data. As I presented before, we don't expect just be able to exchange data from software to softwares. We would like to have the data at a central position and be able to retrieve it. So this can be done with APIs, but of course, we have to find some kind of common languages and formats in order to make it happen. So the idea is, to have some findable and accessible data. So the API is here to make the data accessible. When you find it, you should be able to see which kind of formats you can use to use the data. A more sophisticated picture of it is the idea of, for example, for the observation measurements with the APIs. The idea is you should be able to choose the way you will get the representation of your data. So should it be with the GeoSci YML style or DIG style or AGS style or Building Smart National? I mean, it would depend on your use case, and the idea is the API should be able to propose as much as possible kind of formats in order to fulfill your requirements, in order to enable you to use the data in your softwares afterwards. That's the main concept of this API. A wrap-up of this presentation. As I said, in the Geotech IE, we have some community-oriented goals. We intend to do the connection between scientific IT people, BIM and GIS, and also users and solution providers. These are ongoing activity. You can apply and join if you want and contact me for doing that. The idea is also to go forward into defining some solution with the implementation forum. And we believe that this activity would be a main contribution to this ISSMGE TC222 Objective 2 that is about providing some guidelines and also recommendation for the use of standards. If you want more details about our intentions, there is a white paper that is already available. There is a link that is here that I will put in the chat in order to enable you to have a look of what we do, and if you're interested, join us. This white paper was signed by people interested in the different standards dimensions, so AGS, DIGS, OGC, and BSI. Another information is about the upcoming delivery of the IFC tunnel project and extension for IFC. If you are interested in this thing, please contact Michel Rive and also Jonas Weil, that was the leader of the definition of the geotech extensions. They will be happening in the IFC 4.4. I just pasted what is the estimated date for the delivery of it in 2022. please contact them if you need more information. They may provide you more details about it. Thanks for your attention, and I'm happy to answer some questions in the chat and more things afterwards if you want.
Thank you so much, Mickael. That was very, very interesting. And the standardization part of what we're doing is really, really important. So it's a really nice work that you're doing and on this part. And I think our next presenter is Jelena Ninic. She's going to talk about ongoing research within BIM and DT.
Hello, everyone. Good morning, afternoon, or good evening, depending on where you are across the globe. My name is Jelena Ninic, and I am Associate Professor in Digital Engineering at the University of Birmingham. I'm also Associate Editor in the TUST. Shortly about my background, I did my PhD in Germany on computational and information modeling in tunneling. Then I moved to University of Nottingham, where I was a Marie Curie Fellow and also Assistant Professor teaching building information modeling. And now I'm at Birmingham, also teaching and researching on information and numerical modeling of underground infrastructure. Today, I'm going to talk about ongoing research within BIM and digital twins in geotechnical engineering and tunnel engineering as well. As you can imagine, this is a huge topic, so therefore I won't be able to address everything. I will just pick up on the most important, or let's say more, the biggest research trends, and also maybe on some challenges that we all will have to work towards if we want to be on the frontiers of the I4 industry, also in geotechnical and underground engineering. Here you can see a summary of some buzzwords: BIM, digital twins, machine learning, computer vision, BIM GIS integration, IoT, big data, and all of these topics do not coexist on its own. They are all interconnected because all the research and development and innovation that is happening around this topic basically all has one meaning. So we have a huge amount of data that is collected through projects, research, and so on. And what we want to organize this data and create an information, and then analyze this data and extract some knowledge out of this information. And when I was preparing for this talk, I went on Scopus. This was 4 days ago, and I was searching how many research publication we had from 2008 to 21. I excluded 2022 because the data is, of course, incomplete. But you can see that number of research papers on BIM and digital twins for underground engineering, for tunneling, or for geotechnical applications like foundation slope geotechnical engineering is exponentially increasing in like last couple of years, and I expect this trend to be followed. So there is a huge amount of research out there, but what is important for us as researcher, what is important also for practitioners, and for instance also for me as editor, is that we actually find these research papers, trends, tools, methods that are validated and robust, that are also reproducible, because it's sometimes difficult to find something that is easily reproducible, and most importantly also that is scalable. So we don't like to see methods or tools that are applicable only for one set of data or one project. We would like to have tools that are applicable for wider range of problems. So let's start with some definitions. What is building information modeling? Just to put everything in a context. According to a British standard, this is the process of designing, constructing, or operating a building or infrastructure asset using electronic object-oriented information. Definition of national BIM standards in US is slightly different, but is actually addressing completely the same thing. So it's always about digital or electronic information that is developed and updated throughout the project life cycle. And what is digital twin? Simply said, this is an exact digital replica of a construction or construction project or asset. Now, let's look how BIM and digital twin actually relate. So on the right-hand side, you can see one of the digital twin architectures. There are many, but I've just picked this one to show some typical layers. At the bottom, we have physical layer with devices and sensors. Then we have number of layers, which are about data transfer, data storage and management, and communication layer. Then we have this model layer where we actually have this digital model. And then on the top, we have application layer. And this is the layer where number of application like numerical modeling, physical modeling, machine learning, and so on can be used to actually extract the knowledge of this data. So if we want to see what is where is BIM, so BIM model on its own could be seen as just this one of these layers. So it's a kind of subset of digital twin. And what is not BIM or digital twin is that model is just, if you have just 3D model of an asset or whatsoever, this is not BIM or digital twin. Or if this model does not support behavior, Mats was already talking about how when we update one parameter in model, everything should be automatically updated. If this doesn't happen, then this is not BIM. Models that are not used for collaboration. We have a lonely BIM. So if you want to create a BIM for your own purpose, but this is not the true sense of building information modeling. And models that are not updated throughout the life cycle. And now when we know where we sit, I just want to address several topics that are very important, let's say, for geotechnical engineering and for tunnel engineering. And these are just some selected topics. There are many more out there, and we would need probably additional workshop or several workshops to address them all. So today I will just talk about ground modeling of underground structures, BIM-GIS integration, although Mickael has already addressed this a lot, sensing and monitoring, interoperability, and application layer. Starting with ground modeling, there are many tools out there that have been developed that automatically generate digital models of ground using borehole or testing data, but there are a number of challenges to address. So for instance, how to manage and store this borehole and testing data, because we know that we have many sources of the data, many databases, however, they are not coherently organized and this data is not coherently described. And then also how to describe the uncertainties in the ground. This is something that is what is not typical for BIM in construction or for above ground structures. However, ground is quite uncertain. How to create 3D geological models, how to georeference these models, and also how to create interactive, user-friendly visualization and data management systems such that we can actually use these digital models to understand better the underground and to actually support decision making during the design process. Once we have digitally modeled the underground, we also have a number of underground infrastructure that should be modeled. And in capital projects such as Crossrail, it was proven that this digital counterpart was very important actually to run smoothly the physical construction project. And while in many design tools, BIM tools, you would already have elements like foundations, drainage system, pipes, and so on, there is a number of underground structures that are not available. So there is lots of research going on in digital or parametric modeling in order to develop these components as well, such tunnels, underground stations, etc. Mats already was talking a lot about it, but yeah, the beauty of BIM is that it has grown out of parametric object modeling, and that we can develop these classes of all prefabricated components or all structures that are having these very clean geometries, then implement these functionalities and actually very easily explore different design just by changing these parameters. This is also shown here for prefabricated underground stations as well. Another topic, again, Mickael was talking a lot about this, is BIM GIS integration, because both GIS and BIM are associated with the information repository for data management. Only there is a difference, because BIM encompasses detailed project information and GIS is manipulative management of geospatial data. So it's data management in the broader sense. And each can benefit from another. BIM is benefiting, of course, from GIS because we can actually visualize and analyze our projects within the context of natural environment. And at the same time, GIS is benefiting for our BIM data, because we have we can contribute with the detailed information and analysis from BIM and actually evaluate impact of this project on the environment. When I was talking about this digital twin, very important number of layers were related to physical layer, sensing, monitoring, and actually acquiring the data. In geotechnical engineering, this is particularly important because of uncertainties that we have associated with underground and topology and so on, and parameters. While there are a number of traditional geotechnical sensing and monitoring, let's say, techniques for acquiring data that can be easily, let's say, also implemented in digital models. There are many new advanced sensing technologies coming up, and such sensors in tunnel boring machines, or for instance, satellite data, ground penetrating radar, imaging, laser scanning, fiber optic deformation sensors, and most recently also quantum technology sensing. And here you can see actually some of these technologies, how they are used actually to, first of all, of course, to acquire some data, and then some advanced technologies. In general, machine learning is very often used to actually back analyze this data and quantify these uncertainties or in underground. Another topic also very elaboratively presented by Mickael, so I won't spend too much words on this, is interoperability. BIM is typical for many large number of stakeholders that should collaborate throughout the whole project life cycle, from initial design, conceptual phases, over design, construction, operation, maintenance, finally to demolition. So number of stakeholders working with different software, with different data formats. So it's very important to have a common language. And industry foundation class is one of the standardized data formats. However, there are many other that Mickael already mentioned as well. And as also Mickael mentioned, there is IFC Tunnel 4 based on version 4.4, and I've seen many development in this area. It's important to say that all these data formats are not developed for all possible use cases, but only just for some certain selected use cases. And as you can see, among these selected use cases, geotechnical modeling for design, construction, and maintenance, and general geotechnical modeling is a very important one and selected with a high priority. However, for instance, structural and geomechanical analysis are identified for now as a low priority for development. And now I'm coming to the part which is the most exciting part actually for the researchers, and this is this application layer on the top. So how we apply different advanced techniques, cutting edge research methodologies to extract knowledge out of this information that we have stored in our digital models. There are many different applications. I'm going to address only integration with numerical modeling, machine learning for prediction, and computer vision for inspection and maintenance. Integration with digital models and numerical models is designed to design use case. And for instance, in current IFC tunnel is not included because of the challenges associated with it. And there are challenges when we want to integrate numerical models with digital models. For instance, like numerical models don't have standardized data formats for importing the geometry. There are a number of things like boundary conditions, mesh generation has to be, let's say, manually sometimes adjusted, and how to how to post-process these huge amount of results that we obtain from the analysis in a seamless way. However, there are opportunities as well with that regard. First of all, either pushing numerical software vendors to also adopt these standardized data formats. This is one option, but the second option is to go for open source platform with using advanced numerical methods such IGA and CAD/FEM. And this is the research also, for instance, I'm working on. And this is actually, I think, the way to go forward. Here is the example of how we integrate numerical modeling and design models in fully automated way. First of all, we have here fully parametric BIM model for tunneling, for segmented tunnel lining. We can just change these parameters and generate a design, export automatically all geometry and semantics, and then use advanced numerical methods such isogeometric analysis to generate and analyze these tunnel lining designs. By using IGA, we don't need to generate a mesh because we actually automatically using NURBS from design models. Hence, this 300-meter section was both designed and analyzed within less than 10 minutes, which is amazing speed. And also we can use it on a for much more holistic, let's say, models that integrates everything: ground, city models, lining, TBMs, and so on. And another advanced numerical methods such as CAD/FEM could be also used because they are very numerically efficient. So even kilometers long sections could be analyzed, designed and analyzed very quickly. And the last topic I would like to address is artificial intelligence for prediction in geotechnical engineering. Artificial intelligence is a broader term, and it encompasses machine learning, computer vision, and robotics. It's used for many applications like soil properties prediction, settlement deformation prediction, process steering, back analysis, and so on. And it's used for a reason, because machine learning is very powerful for processing this huge amount of data that we are actually acquiring during our geotechnical projects. I already mentioned number of data sources that we can have, and using techniques such as deep learning, we can actually have a different type of machine learning, either learning from monitoring, learning from waveforms, even learning from images. We are able actually to process this data and extract knowledge to predict settlements, parameters, to evaluate, for instance, to diagnose the conditions of our structures. And here is one example where waveforms are used, for instance, to back analyze the fault zones in the ground. And this is a second example where actually machine learning was used to predict damage on the existing structures depending on the position of the tunnel. So basically, this prediction is done in real time based on trained machine learning models, and we can easily now change any parameters of this model of position of building with respect to these tunnels to see what is the effect of tunneling on that building. And then one of the last things that I want to address is how we can use also machine learning for inspection and maintenance. Deep neural networks, particularly convolutional neural networks, are one of the breakthroughs in machine learning in last years. And we can use CNNs to learn from images. So for instance, we can use it for either classification of or localization of the damage in the structure. So if we have trained machine learning models, basically what we can do, we can go to our structures, take an image, and our machine learning algorithm could classify and localize the damage automatically. Or we can go a step further and do the semantic segmentation, where we can actually even define see the boundaries of this damage, like binary classifier, or even like with multi-classes. For instance, this is a spalling and this is exposed reinforcement. In order to bring everything together, what I want to mention at the end of this presentation is one facility that we are fortunate to have here at the University of Birmingham. This is called National Building Infrastructure Facility, and BIF. And it has been built and established recently, and encompasses more or less all the technologies that I have previously mentioned: digital twins, robotics, real scale testing, even quantum technology for sensing. And what we are able to do within this facility, we are having a real scale test. As you can see this here, like this is buried pipe, and then we have digital twins of these tests with all sensing. So when this is tested, we can control it via digital twin and basically manipulate our real scale testing. Same is for instance, for the soil structure interaction, where we have a huge actuators where we can actually apply the settlements and then also control, let's say, some design parameters in order to, let's say, provide minimum impact on our structures, underground structures. Thank you for your attention, and looking forward to discussion later. And for any questions, of course, you can also contact me.
Thank you so much, Jelena. That was really interesting. These digital twins for the underground construction. That's really cool. Then next up is Raymond, if you are ready.
First of all, thank you, Chairman. I'm Raymond Koo from the Hong Kong government. It is my great pleasure to share my experience with all of you. The topic now is going to talk about how we adopt BIM and digital twins in our geotechnical engineering projects. First of all, I would like to share with you the current geotechnical information infrastructures developed in Hong Kong. The framework is quite similar to what Dr. Ninic just presented. And then I will going to present two examples of BIM and digital twin technologies. And they are called smart landslide debris resisting barriers, which is used to detect any landslide impact on our mitigation measures. And the second one is the pole-shunt drainage tunnels, which is used to drain down the underground water to stabilize the slopes. And the next speaker, Mr. Simon Leung, he will present another application of a mega tunneling project in Hong Kong as well. And last but not the least, I will also show you the digital design automations for an example of a slope upgrading works methodology. So part one, the setup of the geotechnical information structures is quite essential. And from the speakers we just learned today, we know the BIM workflow and the integration with the GIS or digital twin is the first step, like we want to linkage all the useful information data. And today I'm going to show you the established data infrastructures, how people in Hong Kong or the government to contain and to process and to analyze the available geotechnical data. Through these integrated infrastructures, we can utilize the core technology of BIM and GIS informations. Some data we established in Hong Kong, they are even a real-time records, such as rainfall data, slope groundwater measurements, the landslide impact signal, and even some blasting data on real-time during the tunneling works. And actually, why we're doing this is because we want to build up our access management to monitor and to model and to contain all this data through day-to-day projects, and we can utilize this as an important access for build up another new projects. And we also have a vision to share our data with our partners in the industries and also the publics. So this knowledge will be sustained and transferred to projects and be very important, I would say, milestone for the government here to move to the digital world. Right. I'm going to share with you some example of the spatial data we contained here. We have quite a large amount of the geotechnical informations. For example, the rainfall data, because you know the Hong Kong region is always hit by typhoon and some tropical climate, and lots of the rainfall would causing all the landslide problems and the hazards, the debris flow in Hong Kong. That's why we start establishing the geotechnical data from all the rainfall data in order to correlate the landslide distributions and the susceptibility maps. And all this will be integrated into one single platform. Another important data we got is the annual aerial photos and the DTM, the digital terrain model, and also the associated adjacent building structures. This is all the data we utilize for planning our project and to formulate a design or to identify any potential landslide hazards to our development of infrastructures. As I mentioned, in Hong Kong, we also have a policy for open data. And actually, we allows our local consultants and our publics to access our data, of course, except those information with restricted privacy. And they can browse our website and to download these open data, such as the borehole AGS data, the LiDAR topographical data. These will be freely available on our infrastructure system. And this slide, I would like to share with you what the layout of our integrated system look like. It could be viewed by either 2D or 3D format. And you can also cut some sections and do some site measurement, like virtual measurements for the slope height or measure distance to your concerned buildings in the vicinity. And all the available registered mimic slopes or retaining walls, structures, underground utilities, tunnels could be found in this integrated database system, because all the government department in Hong Kong will work together and put their available informations, the SBU's models, into these infrastructures. And people from the local industry can actually access this information to quickly grab what sort of existing utilities they're going to be faced or will affect their projects. We recently also extended our web, I would say the web services into both internet and intranet. Of course, in our intranet system, it will allow us to put more like internal government information, such as the land use applications and project progress data. And these services are recently extended to I would say, mobile devices services. And it will allow our user or our local industry, the practitioners, to access our information in a more convenient way. And you can see we have some category in the mobile, we call it Geotechnical Information System, G-Info. And we contain all the basic information, the G-Info map, the landslip warning when there's a typhoon and heavy rainstorm. We will issue the landslip warning and people know where it's going to rainfall to hit, in which part of Hong Kong, and any landslide have been occurred, and send the alert to the local residents. And we also contain all the previous hazard map for those landslides or the hazard or boulder fall for our consultants to utilize this information when they're going to build a new bridges or residential development. And I will also talk about the recent launch smart platform for the IoT detection system, which will be covered in later part of my presentations. And now you can look at the format of the cell phone. Actually, you can locate where the register Mickael slope and the adjacent building. This is on the 2D layout. And there's a pull-down menu that allow you to see all the available informations. As I mentioned, maybe the landlord informations, the maintenance informations, or the near range gauge data. So after I introduce the, I would say the format of our integrated system, I'm going to move to my part 2, which is the applications of BIM and digital twin. So once we establish this framework and the integrated system, we can do a lot of things, like we can put the sensor on our mitigation meshes, and then to monitor it, and through this system, we will get the response as a function of a digital twin. The first one I want to talk about is the smart landslide debris resisting barriers. Basically, we use some sort of barrier to protect the local residents from the hazard of the landslide or the debris flow from the drainage lines or the crest of the hillside. And the barrier actually equipped with the real-time IoT sensors, such as I would say the wireless impact switch. That means when the landslide hit the barrier, we know there's something happened on that locations. And we also, for the research purpose, we also monitor the landslide impact fault depth. And this whole system is self-supplied by the electricity using the solar panels, because you know, some areas are quite remote and we need to rely on the self-sustained power supply system. And it also allows us to reduce the maintenance effort. And we also attach with the real-time digital camera. So when there's a impact switch, we receive the signal, then the camera will be switched on to allow us to review more clear the actual situations. And since we talk about the integration between the BIM and the digital twins, all our mitigation measures will be associated with a BIM model behind. And the BIM model actually will contain all the attributes, the important informations, say for example, when this barrier was built, and also what sort of maintenance service that it needs. And also it tells the people what will be the capacity of this retention barrier that able to capture the debris. If we're going to have a risk of overflowing, then the designer and I would say the maintenance party will have to know to have some sort of follow-up actions or immediate emergency work. And we put this BIM model into our integrated system, as I shown that in the first couple of slides. And basically, you can just browse our integrated system by your cell phone or internet version. You can locate, for example, if there's a hillside or the road access road here, you can locate and find what sort of measures with the digital sensor that you got. And same, we try to make it more user-friendly for the user. We put all these smart sensor to equip with the cell phone technology, and people can do it outside in the field, and to access what the performance or the current situations about the function on the, I would say the digital twin feature, you can actually manually switch off the camera by this smart cell phone to locate what your interested part and to see. And from this slide, you can see those sensor will be located, and you can touch the sensor on the cell phone to find where you want to see. Another example I would like to share, because due to the limit time, I would today just share two examples here. The second example I want to show is the Boshan drainage tunnels. This project actually was complete around, I would say, 15 years ago. And recently, we put all the IoT sensor into this drainage project. The purpose of this project, you can see we have built a lot of the sub-vertical drain here in order to drain down the underground water to protect the residential building on the downhill side. Because back to, I think, 40 years ago, there's a major landslide and caused over 150 people casualty for this incident. So that's why our office built a drainage tunnel. And recently, we also adopt the digital twin technology to monitor the pressure acting on the valve of the sub-vertical drain. As you can see in on this slide, the pictures, this is the tunnel inside, and we built up with a digital twin model to monitor the performance of the groundwaters. And actually, when the pressure which our target triggering level, will then switch on the drain water valve to allow more water to drain out to lower the groundwater level. And that's the function that we coupled with the BIM technology and the real-time monitorings. And we use the same integrated platform to put this smart system. Sorry that you cannot see the the tunnel here, but this is the building we are going to protect. I would say at the downhill side, and you can use this integrated system to get all the informations for the tunnel and the adjacent buildings. And we are going to do more this type of mitigation measures in our coming infrastructure projects in Hong Kong. And to give you a bit more to taste the model, I'm going to show you this video clip. You can see we put the BIM model with the inferred geology, and you can click this sub-vertical drain through the integrated system, and actually you can download and to see what the pressure data you are interested, and check your target level. And basically, you can plot the groundwater surface. One is the purge water above the separate, and then the other groundwater layer is within the bedrock. So it allows us to understand more the correlation with the rising of the rainfall with the geology and the BIM model. And as I mentioned, if there's a alert exceeded our target level, the maintenance department will receive the signal, and they will have to do some emergency work or some sort of review of the situations as planned. And last but not the least, I would like to introduce another methodology that in Hong Kong, how we use the digital technology to design or to carry out the slope stability assessment. To make it more easy to understand, I also make another video for you. So this is a terrain model with the geology integrated using LeapFrog, the program. And basically, by building up the geological model or even some core stone at the yellow spot there, you can build up your geological model. And this model also allow you to determine the critical sections, and then you can use this section automatically put into the substability assessments. And all this process could be automatically used instead of previously we do the separate manual and then cross-section cutting and then do the calculation separately. So basically we are going to migrate all our design work into the coupled BIM and digital technology. And I think this is what I want to share today, and welcome if you have any questions. Thank you for listening. Thank you.
Thank you so much, Raymond, for a very interesting presentation. The next up is Simon.
Yeah, thank you for the invitation. Before I start, I'd like to introduce myself. I'm Simon Leung, AECOM. I'm very grateful being invited for this presentation here. My topic today is innovation application for mega project. The project name, a number of you may have known, is the relocation of Sha Tin sewage treatment works to caverns. So the project introduction, I'd like to pass on a few slides to my colleague Elton from DSD. Thank you, Elton.
Thank you, Simon. This is Elton from the Drainage Services Department of Hong Kong SAR. We are driving the initiative to relocate the existing sewage treatment plant, the one that you saw in the pictures in here in the lower part of pictures, to the across the river, the Shima River, into the mountain in the cavern that we are currently construct, which will be complete in a few years, within a few years. We take the opportunities of this project to promote the use of BIM in the public works, and we hope we take these opportunities to continue our commitment in promoting the use of BIM in the mega projects like this one. The remaining presentation will be given by my team member Simon, who is an enthusiastic engineer and passionate in helping to push the boundary of applying different innovative technology in the construction. So I'll pass the stage to Simon to walk you through the remaining of this presentation. Thank you.
Yeah, thank you, Elton. Yes, thank you, Elton, for the introduction. And you can see from the pictures here is the sewage treatment works is on the bottom side of this photo here. My project team's job is to relocate everything within that green dotted line from the right-hand side of the Shima River to the left-hand side inside the cavern. Okay. Elton explained a little bit that this cavern includes 5 parallel caverns. The span is 32 meters wide, is very much wider than a normal tunnel in Hong Kong here. And the maximum height is 38 meters high. So you can imagine how massive the cavern that we are facing to construct for this project here. So the method we achieve this project is by the drill and blast excavation, because drill and blast, as compared with the tunnel boring machine, is the low investment cost, higher adaptability, and large flexibility. Okay, but with a mega project like ours project here, locating in the urban area of Sha Tin area, we face a number of challenges. This is a mega size project in Hong Kong here. In this project, the duration of this project lasts for more than 10 years. It's a very long duration. High complexity, because why I say high complexity, because inside the cavern, within a very small area, we involved a number of disciplines like geotechnical, tunneling, civil discipline, electrical and mechanical, things like that. It's all these interface discipline cause a lot of challenges to us. Sensitive receiver, and multi-phase basting. The two number of challenges that I want to highlight here is the sensitive receiver. The project here is located in between two very sensitive receiver. One is the Chevalier Garden and one is the Fisherman Village. And this sensitive receiver, this residence here, is just less than 100 meters away from a basting site. You can imagine every time that we bast, the vibration, noises, air pollution, things that cause nuisance to the neighbors. That's why we have to pay a particular attention to control to the acceptable level for them. Because we have a very large basting phase, we have to conduct a multi-bast, unlike the traditional tunneling method from one bast per phase, but we have to divide up several 3 to 4 basts per phase. And for this reason here, we have to tackle a very complicated logistic problem to mark out all the excavated rock. And for these challenges here, how do we do that? How do we overcome the problems here? Then for this mega project here in Hong Kong, we have to innovate. We have to apply a number of innovation items, technology to tackle all these problem here. Okay, we have in this project here, the project team, DSD, contractor, and AECOM has innovated a number of activities ourselves to push forward the development of the carbon development. We have developed 9 number of them. Now, let me go through it one by one. BIM in Hong Kong, there's a technical circular requirement, a government requirement that we have to adopt a BIM together with the DWSS system already. But for the integration of DWSS system and the BIM, that's a run problem because in Hong Kong, every BIM model, we have to upgrade it or update it version by version. But however, every time that we update a BIM model, the integration, the hookup will be lost because the old model you have all superseded by a new one already. But we created a node to hook up the DWSS system to a node, and that node is actually XYZ representing a location of the BIM model. Whenever you update a BIM model, you will not lose the file. You will automatically attach to the new version of the model. That application can actually save a lot of time and resources of the supervisory staff. That's very good application that we're using it for this project here. You know, this innovation project, we use the rockbowl system. Sometimes a rockbowl system treated as a temporary measure, but in our project, there's no concrete lining for it. We use the rockbowl system form part of the permanent structure. So the alignment and the position or the direction of the rockbowl becomes a very important information for ours. So we have to provide, how do we provide the exact alignment of it? So we have developed a drill to beam system installed in the jumbo machine. Whenever you drill a rockbowl inside penetrating through the rock, the alignment and the position will form a beam model. They form a beam model automatically. So we have more than 1 million rockbowl installed in this cabin here. So for every time we penetration through the rock, we have formed a beam model already for this rockbowl system. That saves a lot of time for the supervision and as-built drawing as well. Second innovation that we introduced in this project here, we call it HoloLens. There's form 2 parts of it. One is the hardware, and the second part is the software. The hardware is just the HoloLens. It's just like a helmet shown on the top right-hand corner. But the buzzword, the gravity of using this HoloLens is we implant some BIM model. We use a filter to implant some BIM model inside the virtual reality of it. What we call it is a mixed reality. But how do we use it for the basting supervision? Probably a number of you knows that every bast that our supervisory staff have to check the number of bast hole, the position. We have to confirm the positions are correct. The number of bast holes are correct according to the basting design. But in reality, that usually very short time for the supervisory staff to check all these items, all these tasks. That's usually limited time or even not enough time for them to check it. So every time the contractor submits the BIM, the blasting design, we transform that blasting design into a BIM model filter. Then we implant into the HoloLens here. So our work supervisor just bring this HoloLens outside to the blasting phase, put it on their head, and see through the glasses there. And the image of the blasting design will appear on the lenses inside the caverns. So what do we do is it's just like what do we see? It's just like the top right photos of it. The number of blast holes usually more than 200 or even 300. You can just identify the number of blast holes in reality inside the blast phase, rather than in the traditional way you count it one by one and count it takes a lot of time to counting it. That's a very big improvement in supervision, especially the blasting supervision. And other application that we used it with the HoloLens is the utilities management. You know, Hong Kong utilities everywhere is very congested, and usually that utilities diversion cause a lot of time delay, things like that. But we put the utility diversion or the as-built utilities onto the real reality. So our work supervisor or frontline worker put on this helmet, put on this HoloLens, they know exactly where the utility is in the very exact location. So whenever they excavate the ground for the utility, they know exactly where will be the utilities, so they can avoid it to damage the utility. That can enhance the safety as well as the blasting phase supervision. Well, of course, we have introduced a number of innovation like DWSS system, BIM model, and we use the mobile apps inside the cavern, but inside the cavern, there's no network. So we have introduced a site-specific 5G network inside this cavern here. We install a number of base stations outside and inside the cavern. So all BIM model, all messages, and all DWSS system, inspection form, things like that, we can do it immediately with very low latency with the 5G network. And that's very important facilities to facilitate our innovation. So we come down to a robotic application. Well, we're doing the blasting during blasting for the whole cavern project. Traditionally, you know that every time after the blasting, that is the ventilation problem. There's only one person allowed to enter into the blasting phase right after the blasting. That's called a short fire legally. So even though we know these blasting activities is very dangerous activities or high risk activities, but we don't want to commit a human being to enter the very high activities area here. So we innovate, we introduce a robotic vehicle, what we call it resident site robotic supervisor. This is the self-manned, self-autonomous vehicle. They can drive it along the road itself. So what we do with this is after the blasting, right afterward, before the short fire to enter into the cavern, we send this robotic vehicle to check, to take video, to take photograph, to help the software to predetermine where there is any misfire, things like that. And that's one application for this RSRS here. The second application we have been using is you see that top bit here, the top bit that is actually the air monitoring machine. I will introduce in the next slide then. You know that after the blasting, that is the ventilation problem. There's the toxic gas, things like that, lack of oxygen, things like that. Then you just drive this machine here automatically without committing any human being inside the cavern. Before that, we send this robotic inside the cavern. So they measure the air monitoring. They send the message through the 5G network to our mobile network. So that's the second application. The third application that we used it with this robotic machine, you see that top bit, the black stuff is actually the LiDAR, the 3D scanner. We will scan through the rock map surfaces to form the heat map. So we know exactly where the rock movement will there be any slight rock movement, then we can predetermine that any sign of collapsing or sign of falling of the rock pieces, things like that. That's 3 applications that we were using that with this robotic machine here that will be developed further for this. Okay, I'll show you a video on the left-hand side. You see how we operate in contract 1 of this project here. 3D scanning, we form a point cloud, and these are the measurement of the air monitoring. Okay, I will. On the right-hand side here, you will see the 3D scanning with this resident site robotic supervisor. That's the point cloud image that formed for us to monitor. Okay, I mentioned earlier that we have applied the air monitoring with this robotic machine. Apart from the traditional 4 measurement, CO, oxygen, LEL, and the H2S. That's the mandatory that we have to measure under the contract requirement. Apart from that 4 specific requirement, that air monitoring we measure actually 9 measurement: radon gas, lighting, lux level, things like that, as shown on the bottom left-hand corner. Why this air monitoring is very useful for the cabin development? Because we install it in the robotic machine. They walk along the cabin, it measure the measurement. It sent through the 5G network. We can actually see the measurement in the tele rooms. Also, we can see this measurement with a mobile app, iPad, or even a computer in my office here. So it's actually introduced the supervision anywhere and anytime. So that can improve the safety and the efficiency of the cabin development. So quite a lot. Okay. We also introduced AI for a number of safety measure, setting up some restricted zone, AI monitoring to prevent any unauthorized entry to this restricted zone, PPE, whether our worker or our supervisory staff are wearing the proper PPE, helmets, things like that. If they are not wearing a helmet entering the site, it will just shout out, give you some beep sound warning, things like that. Entering a restricted zone with the machinery moving, it will give you a warning or sign of warning or SMS message as well. That measure, AI measure, is also improve the safety of the site management of a mega project as well. So with the blasting specifically that we will do it, we introduced also measure while drilling. What is the measure while drilling is simply the name, measuring the data while the jumbo machine is drilling the rock. It tells you a lot of geomechanical data, geological data, and also the hydrological data. Each blast hole drilling will give you a set of data like the rotation force, the thrusting force, the things like all the fractal factor, water index, things like a lot of geological data they can give you. And also this measure while drilling is actually you doing the drilling on site and send the message or the information is sent from site right back to the office here, or even a logbook. Whenever I have a network, I can live monitoring the drilling on site. So it's also introduced this concept of supervision anywhere and anytime here as well. So another innovation technology we apply for this cabin development is because nowadays the overbreak of the rock becomes the byproduct of the blasting. It easily happens, commonly happen, 5% to 10% is commonly happen because the overbreak is all depends on the joint and things like that. And we have identified 11 set data in terms of the geological data and blasting data. For example, MIC, advancement factor, joint set, water index, things like that. All these factors affecting the overbreak of the blasting. So now we have identified 11 number of parameters that will affect the overbreak. So we use the AI setting up an algorithm, AI engine to monitor, to predict the next round of blasting will, how much overbreak will it generate. In turn, how we going to control the overbreak with, control the overbreak with minimum, like setting up less MIC, less advancement factor. So we have an AI to tell us what to do to minimize the amount of overbreak as to improve the efficiency of the blasting as well. So that can be very very helpful to our supervision as well. And for the day-to-day supervision, we have number of work supervisor monitoring the activities. For each blasting cycle, we have 10 activities for one blasting cycle. Our supervisory staff duty is to monitor the start and the end time of each activities as to monitoring the efficiency of the blasting cycle. But traditionally, they use a pen, writing up all this, jotting down the notes, the time into the paper or Excel. But we developed an in-house app to simply just take out the mobile phone, and whenever the activity starts, for example, blasting drilling, whenever it starts, you just press the button start. When you finish, just press the button finish. Then the whole duration of this activity is already recorded in the apps. So that's the full record as has been recorded in this apps here. So it's very easy monitoring the efficiency of the contractor's performance. So that's a very useful access. Rather than putting up in the WhatsApp, you can very difficult to search the information from the WhatsApp. But with these apps here, you can just sorting out whenever you like to take out the information. So it is very convenient and it's easy to find. Okay, we have also developed apps. You know the blasting, right? A supervisory staff, a BCS, blasting competent person. One of the duty is to check the blasting design contractor submitted to us. So what to check before that we approve the blasting design and send it to mines department for ordering the explosive. There's actually a number of items that we have to check, like the void ratio, sectional area, powder factor, breakage angle, delay separation, etc. Rather than check it by hand calculation, we set up apps. Just press the button, input the data from the blasting design. It will tell you exactly whether it complies with the requirement or not. This actually saves time and set the resources and presented as a very nice set of record of checking. So these apps help the BCS to check the blasting design. That saves our time, and more accurate with the formula inside these apps here. So this innovation, I briefly introduced this innovation that we adopted in the Shutting Cabin project. And I can say this is a very useful, in terms of supervision, enhance the time, enhance the quality of supervision. This is the brief introduction of my presentation that we adopted in the mega project like Shutting Cabin here. I hope I can, lift down this PowerPoint here and show you guys that if you find any items that you find it interesting or you want to know more about it, that you can just find me. I can, introduce this item in more details. Okay, that's the end of my presentation today. Thank you very much.
Thank you so much for a very interesting presentation. That was a really extremely large and interesting project to hear about. I think it's the first time I've heard about the project establishing their own 5G network within the cavern. That's that doesn't happen too often. So thank you so much for the presentation.
Yes,
yeah,
thank you,
Simon.
Thank you very
much. Thank you very much. I can leave my PowerPoint here in anything that you find interesting and want to know more about the great details of it. I can drill into the details and introduce for the committee here. Okay, thank you, Raymond.
Yeah,
Great.
Yeah,
Thanks,
perfect.
Simon.
Thank you. Yeah.
Thanks.
All right, bye.
Bye-bye.
As I mentioned earlier, we we sent the questions to 3 persons from around the world and asked them if they could share some of their recent experiences when it comes to BIM and DTs, and perhaps what their expectations are for the TC. Mr. Francois Robida, I think you are on overtime. Is it able for you to start with some opinion here? I know that you're supposed to be leaving some minutes ago, so I'm really sorry that you are a little bit behind on the time schedule.
Thank you very much, Magnus. No, that was very interesting, very impressive presentation so far in this group, and thank you very much for the invitation to say a few words about the experience here in France. Just to introduce myself, so I'm currently the president or chair of the MIND initiative, which is a national project in France where we have more than 60 organizations from universities, public stakeholders, National Railway Authority or metro lines in Paris and so on, and a lot of industrial partners. This project is about the development of BIM for big infrastructures. So moving from buildings to big infrastructures, which is also the topic of today. And we started this project 8 years ago. And one of the focuses of the project was to try to extend the BIM components from buildings to infrastructures, to tunnels, to bridges, and so on. And this aspect of infrastructures have some specificities which are about the impact of the infrastructure and the link of the infrastructure with the environment in general. And of course, geotechnics is in the right middle of this connection between what is built and what was existing before, natural environment or pre-built environment. And so as described by Mickael, it's a place to connect those two worlds of GIS and BIM, who have different ranges of standards, different ways of constructing 3D models. And if we want those people to collaborate together for the short and long term, we need for them to share common models and to share also to define some common standards, not necessarily adopt one single standard for everything, but at least to be able to share information with no ambiguity about semantics. And so this is really important for infrastructures. And so this project, MIND, has done a lot of developments in different areas, including BIM specifications for infrastructures, but also supporting the initiative that Mickael has described for the development of standards for geotechnics across OGC and BSI, and taking aboard the experts of the domain, like the people who have developed the AGS or DIGS, for instance. So this is very important, and for us, for not only for the design of the infrastructure, the construction, but also the exploitation and the long term, we have one of our partners, which is ANDRA, which is a French agency for nuclear waste management. And the topic there is not only to keep the data updated for 10 years, but for hundreds of years. And this means that the information that is collected along the life of the infrastructure has to be managed in a neutral format, and where the semantic is completely described and so on. So this is one of the important, connection of France with your very important initiative, TC222. I would like to mention another one, which is linked to my background. I've been working for the French Geological Survey for more than 30 years. And the focus of geological surveys is really to to keep the information and to build knowledge about the subsurface in a country or in a region. And what Raymond proposed or exposed a little bit earlier today is very, very important. It was originally for mining applications or for groundwater, but today it's about everything which is related to subsurface and connected to low carbon energy storage or waste management and so on. So this extension of the traditional functions of geological surveys to the understanding and management of underground of big cities, for instance, or important areas, the areas of interest, is really critical. So the purpose is to collect data, to make it available to everyone, and be able to reuse this information with for new purposes with new tools like AI, which has been demonstrated already. And this requires, again, the capacity of the different partners and stakeholders to define rules of collaboration. Not everything has to be open to everyone or for free. It depends on the economic model that is selected by the country or the area. But at least there is a need for common standards again and common rules to share the information along the life cycle, and this can be implemented without political issues for all the infrastructures which are built with public money to make available all of the information collected by public money. But this can be, of course, extended to other infrastructures or constructions which are made by the industry. So altogether, I think this collaboration that you have started with this TC222 is really important for making possible the real digital twins that put together a built environment, natural environment, all the different stakeholders. We've at the very center of the system the connection with geotechnics and the capability to put together experts of the domain like geotechnical engineers, but also IT people, and who will be able to facilitate the connection of the people and the integration of their work in this area. So thank you again for this opportunity to share this view from France. And I say hello to some of my former colleagues from European Geological Surveys that I can see on the list.
Thank you so much, Francois, for your opinions, and thank you for your thoughts about the essence of the TC. And of course, we are in very early in the startup of the TC, but much of what you are saying is also what's our thoughts behind the TCs, and we're very happy also to have Mickael, your former colleague from France Geological Survey, as a part of the TC, the nominated TC group. So thank you very much. I think we move on to the next, Dr. Hiromasa Shima from the Oyo Corporation in Japan.
Okay, thank you very much for giving me a chance to say some words about the Japanese situation. So I'm Hiromasa, working with the Oyo Corporation. Oyo Corporation is the largest geological, geotechnical, and geoengineering consulting firm in Japan. So regarding the recent movement in Japanese infrastructure, BIM community and industry, today I'd like to say 4 points. First one is the government initiative. Ministry of Land, Infrastructure and Transport of Japan announced a few years ago that most of the government projects must comply BIM from 2023, that is next year. So that is a big government initiative is going on. Second is Building Smart Japan. That is the Japanese chapter of PSI has already begun software certification program for infrastructure model view definition and planned to include geotechnical model from next year. So IFC interoperability certification program is also coming soon. Thirdly, unfortunately, the majority of BIM community in Japan are still so-called above ground people. And only limited number of people in soil mechanics and geotechnical community are involved in BIM. So that is the kind of unbalance between the above surface people and underground people. But you know, the more than 50% of design change in infrastructure project is coming from underground problem. So we have to pay more attention to the underground. So I believe more geotechnical or geological people must involved in BIM project. And lastly, not least, I would like to say that geotechnical, technical challenge in BIM. Uncertainty of geological and geotechnical model is crucial, as you know. But such uncertainty described only qualitatively now. Quantitative expression of uncertainty in the geotechnical model is absolutely necessary for infrastructure BIM. And it is our inevitable challenge. So we need quantitative assessment of uncertainty for BIM. Okay, that's the whole point I would like to say tonight. Oh. Thank you very much.
Thank you so much, Dr. Shima. Sounds like Japan and my home country, Norway, is quite similar. I think the BIM development above ground is way in front of the BIM development underground. What you also mentioned about uncertainty, that's something that we at NGI also have worked with. It's difficult to communicate, but it's extremely important to communicate and make sure that everybody that uses the models actually has the uncertainty in the models into account. A given surface or line or a color is very easy to just take into use for other people working on the same projects. So.
Yeah, right.
Yes, but thank you very much, Dr. Shima, for some pickups from also some information about the status in Japan. You said that the government says that all governmental projects should be BIM-based in 2023. How is the standardization when it comes to BIM for these projects? Is that development also aligned with the demands that you have to deliver all the projects in a BIM model, or is that also something that's a parallel development that is really has to finish before 2023?
That's a good question. So we cannot suddenly change from old style to new style. So there must be some transition period. But and also there is some exception. Government say in general, all projects. But in general means there is always some exception. But anyway, next year we have to build a BIM model, and we have to provide that such BIM model as a final result to government in electronics data as electronics data.
Okay, thank you.
Welcome.
Thank you again. Thank you so much for your sum up from Japan, Dr. Shima. And then I think we move on to Dr. Derrick Dasenbrock.
Thank you for the invitation to talk a bit about US practice. So my name is Derrick Dasenbrock. I'm a geotechnical engineer with the United States Department of Transportation's Federal Highway Administration. previous to my job here, I worked with a state DOT. So all of my work has been in transportation and horizontal construction. So that's going to be, principally what I'll talk about as part of the U.S. practice. I think in the horizontal construction, we're somewhat behind in BIM and digital twins compared to some of our colleagues in buildings, vertical energy, and other sectors. But we're starting to make progress. Particularly in other disciplines, just in the nature of the above ground work. So it sounds like that's similar to Norway and Japan's experience. So one of the other things I'm involved in is working with the American Society of Civil Engineers, GeoInstitute's Technical Coordination Council, and the DIGS Working Group. So I've been involved in the DIGS group actually since its inception as a transportation pooled fund study with the Ohio Department of Transportation back in 2006. Minnesota DOT was a partner to that project. So been along for the ride there for a comparatively long time. So recent developments of the states in the transportation sector. One of our groups that develops standards, the American Association of State Highway and Transportation Officials, has adopted an administrative resolution adopting industry foundation classes and the IFC schema as the standard for data exchange. There are two what are called pooled fund studies with nearly half of the US states involved in each of those for building out IFC related to transportation projects for bridges and for highway infrastructure more generally. Most of our work is still currently in 2D CAD design, I would say. There is a move toward 3D design, particularly for what I'll call complex structures. So if that might be like hydraulic storm surge facilities, complex curved steel bridges, infrastructure for alternative procurement projects through design build, P3. A lot of the work for that is now 3D design because it's often simpler to do for larger projects, and there are economies of scale associated with that. Right now, a lot of work in geotechnics, and I'll say for like 3D and not quite BIM, but kind of sort of with digital twins, is in the visualization space. Some of that is now, I'll say, in the design and analysis area. Some of it is more similar to just public involvement and showing what alternatives might look like and problems with construction, particularly for slope stability applications. But things are changing and evolving relatively rapidly. So there's been some work, again, to kind of show the public what might potentially go wrong with projects or designs. Caltrans had a significant effort using HoloLenses to display alternatives for their last chance grade along the Pacific Coast Highway where a large slope failure had occurred. And visualization is, I'll say, a current trending topic, as much in the geotechnical sector, really, as BIM and digital twins are. There's an upcoming symposium that our Transportation Research Board is hosting in November, a specialty conference, and there are discussions about 3D modeling and augmented reality, linked updates from field instrumentation, visualization and 3D geostatistical applications. You can imagine, kriging and other types of AI and machine learning for interpolating between borings, and also visualization of movements. There's a lot of work currently in change detection using LiDAR, INSAR, and other technologies, again, mostly for slope stability applications. You may have heard, we've had a lot of wildfires, mudslides in the Western United States. So applications related to the impacts of those types of extreme events on transportation infrastructure is also of interest. And I imagine at some point in the future, those will be modeled in the BIM and digital twin space, but we aren't there quite yet. Most of our work, I would say currently with a lot of practitioners, is working, as Mickael mentioned, with the DIGS XML interchange standard. And we're moving forward now somewhat faster than we have been since its early development, which is exciting to see. We're seeing more vendor and service provider interest and buy-in, and through the ISSMGE Institute, there's some special projects to extend the schema. So it was originally developed mostly for borings and soundings. We're extending it now into geophysics and 2D grouting, and some construction control, test piling, measurement while drilling is one that's been sort of, I'll say, sponsored and may move forward. So we'll see how all that progresses. As far as expectations, I and my colleagues are definitely looking forward to what TC222 is doing for insights and collaboration. It looks like we have a lot to learn from just from today's presentations. So I think a very exciting time in geotechnics, especially because a number of US state departments of transportation are also moving toward digital delivery at a rapid pace. Some states have between 2023 and 2025 as milestones for implementing three-dimensional design, if not BIM and digital twins, but at least 3D CAD files as the bid documents for tendering or letting projects. And so one imagines there will be an expectation that geotechnical information will be in those design plans. And it's going to be a heavy lift, I think, for a lot of US practice to make that happen. So we'll see how it goes moving forward. Thank you.
Thank you very much, Derrick, for that sum up. Sounds really familiar, the last thing you said there. I think we had the same in Norway. The stuff underground being the last part of the project that's really pushed into 3D. If you're going some years back, but yeah, luckily this has changed over the last years, but we're not going very many years back before we did this. Everything underground was just like left out of the 3D models. You said that a lot of this CAD, it's still a lot of 2D CAD design. Is it the demands from the clients who will have to be there to manage to change to 3D? Like you said, some of the states will now have demands that they have to implement 3D in the bid documents, or is it also resistance in the companies doing this, that they are familiar with the 2D, they still want to keep doing 2D because that's the easiest and that's something that they already know, kind of? Or is that maybe difficult to answer?
Well, I would say it really depends, I think, on the size of the projects and the contractors dealing with them, and just institutional practice. So I guess the best way to say it would be everybody in the transportation sector is, I'll say, experienced and accustomed to an 11 by 17 printed plan set of the plan sheets and cross sections at regular spacings as a component of those documents, plan and profile and orthographic views and specifications. And states did embrace moving from large stacks of published paper copies to PDF and other electronic, static images. Some states I quite possibly still use paper. And for smaller projects and for contractors that maybe don't have a lot of electronic equipment, it still may make sense for larger projects and where contractors are bringing to bear, automated grading equipment with a lot of GIS compatibility and tablets to the project site and so forth. For them and for some of the larger contractors, I think it's a lot easier to implement 3D and BIM. So it'll be interesting to see if a rollout has something to do with the scale, size, and complexity of the projects. On the geotechnical side, I would say that it's a particular challenge because we have so much interpreted information as opposed to lines on a plan that can be changed easily, I suppose. So, but it will be interesting to see how successful projects are and the type of information, how the metadata is incorporated in terms of risk and reliability and all the attributes associated to different types of information going in the plan set.
Definitely. Again, thank you very much. Mats, I think we had some more questions to the presentations.
We have one more question from me and Vic to Dr. Jelena. I'm not sure if you have read it in the chat log, Jelena.
It's about use of OpenSees for
Yes.
design workflow. Yes, yeah. In general, as some of the participants commented, I mean, BIM should not be one time or like live as a project design lives. BIM models should live as long as the asset lives. And this is why commercial software are sometimes challenging to use because of the of all versions that are coming every year. So I think that the ideal would be to use or develop also open source tools complying with the standardization that is coming for like a description of the components, its geometry, semantics, and so on. And is equally for the numerical software, it would be really good if open source tools are then developed to comply with these standard formats of geometry and semantics description, and to have something which is reliable for years to come to use without worrying what the next version of the software will be. Any type of open software, open source platform such OpenSees, Kratos, I don't know, like there are many others. Yeah, would definitely be a good choice for development of let's say analysis tools.
Thank you, Jelena, for that good answer. We're getting close to the end of the workshop. While listening to the presentations, I tried to just also have a look at the results from the questionnaire. 70 answers. If some of you haven't answered it, just scroll up to the top of the chat, and we will really appreciate it. This is really helpful for us to get some more information about the status. This is of course not what's it? Yeah, I can't find the English word. This is not the correct picture, but at least it's an idea of the status from the participants today. We see that it's the participants today it's really a lot from Europe and from Asia. Because of the time zones, that's not very surprising that our friends in US and Canada and South America and Central America, it's a little off their time zone. Derrick said he's up at 2 in the morning, so we understand that that's difficult, and that's something that we have to consider in the upcoming events. Either we have to find the time spot where we think we can cover most of the world, or we have to do parallel sessions, one early and one late European time, so that we can cover the entire world. Because our aim is, of course, to reach out to all around the globe, not only those who find the time zone correct for them, kind of. It's also nice to see that it's we haven't only reached geotechnical engineers, or there are a lot of people with other education who works with geotechnical engineering. It's a wide span between the background of the people attending the workshop. Where the skill is gained, it seems like a lot of people are self-study. That sounds very familiar for at least me and Mats as well. That's the background. Of course, I think the part for the formal education at university, that is definitely something that is picking up. At least we see it in Norway. That if you go 10 years back, this was not a way to. The educational options within BIM was not very many, and that's something that is increasing. Some curves about which aspects of BIM you're mostly working with, and it seems like the large one is 3D modeling of probably ground conditions, but 3D modeling in general as well. Also interesting to see that we have some which is up on the level where they're using this to asset management and phase planning. That's quite high on the BIM development ladder, so that's good to see. And also quite a lot to work within research and development. 17 persons from 70 answers. That's really a high number. That's good. BIM standards and guidelines and requirements established in the country. Mickael has, of course, talked about this also in his presentation. And we can see that there are several countries that has both national standards or guidelines. I haven't had the time to look into the link between question 9 and 10 so far. But of course, it still looks like Germany is up there. But we have to have a look into that and see what standardization or guidelines which is going on around the world. Mickael had a nice slide early. It's a lot of standards in different countries, but working globally, and we also have to aim for a standard that is covering more than one country or one region or one state. Out of curiosity, we also wanted to do a check on the softwares which is used. Looks like Autodesk still is a popular tool, which we fully understand. But also GIS is also used a lot for modeling and collaboration. I'm not sure if I'm going to go through any more of this. I think we rather just wrap it up. We have 5 minutes left, and we're really happy for the large interest when it comes to the participants who signed up for this. As also mentioned earlier, the entire workshop has been recorded, so we will publish this afterwards. Might be an edited version. The next on the calendar of the TC, we haven't made any plans so far, but we will inform on the ISSMGE TC222 webpage. We will probably also use then now we have the email addresses of all you who has been participating today, so we will send information when we have it. I don't think I have anything more to say. I'm not sure if Mickael, Jelena, Raymond, or Mats, if you have something you want to add.
Looking forward to our future work. I think we have a very exciting future in front of us to engineer.
Definitely, and I think, as mentioned, the interest in this workshop shows how important this is for the future. So that's really cool. I also again want to thank Francois, Hiromasa, and Derrick for their contribution. That was really nice to get some status from France, Japan, and the US. And I think we just say thank you and goodbye, and have a nice day or evening or night or whatever it is where you're living. So, and then I hopefully hope to see you again soon. Bye.